In this question, first things first, there is a typo here, where it should be an N and axioms. Okay. What it's asking you to do is define 3 of the axioms and then verify that this set satisfies those axioms. So we can pick any 3. I'm going to pick one associative, 2, the 0, there exists a 0 in R n such that 0 plus b equals b for all v in R n. And 3, and this associative is the plus operator is associative. 3, let C be an F, or C be an R in this case, because it's R, and X, Y be in R, N, then C box times X plus Y equals C box times X plus C box times Y. Okay, so those are the 3 axioms that I'm going to prove. Now you should know all your axioms, but we're just going to verify these 3. So for associative, we let X, Y, Z be in Rn. What I like to do is before I prove the left side equals right side, I just redefine what X, Y, and Z equals. So then X equals X1 to Xn, Y equals Y1 to Yn, and Z equals Z1 to Zn. Then X plus Y, all plus Z, plus Z equals X1, Xn plus Y1, Yn plus Z1 up to Zn. This equals, and we're going to do, these are box pluses. Box pluses, box pluses. This is by definition of X, Y, Z. This equals X1 plus Y1 Xn plus Yn box plus Z1 up to Zn by definition of box plus, which equals Xn plus, or X1 plus Y1 plus Z1 X repeated up till Xn plus Yn plus Zn, again by definition of box plus. Now here we can apply the associative property of addition. So this equals X1 plus Y1 plus Z1 plus Xn plus Yn plus Zn as real addition is associative. Which equals X1 up to Xn plus Y1 plus Z1 up to Y1 plus Z, or Yn plus Zn by definition of addition operator, which equals X1 up to Xn plus Y1 up to Yn plus, and these should be box pluses, up to Z1 plus Zn by definition of box plus, which equals X box plus Y box plus Z. And we have verified our expression, and this is by definition of X, Y, and Z. Okay, so we have shown that we are associative. Okay, now 3 is going to be very similar. Let C be a real number, X and Y be an Rn. Start at the left side, apply your operators, and get to the right side. That I'm just going to kind of leave this as exercise for you to think about. Okay. Now, question 2 says there exists. Now, this is fundamentally different. There exists, instead of us showing that the left side equals right side, what we're going to do is we're going to consider an object and prove that it has the property we want it to have. So, erasing what we did before. Consider 0, 0 equals 0, 0 up to 0 is in Rn. Let X be in Rn. Then X equals X1 up to Xn. Consider, or now consider, 0 plus X. Well, 0 plus X equals 0, 0, 0 plus X1, X2 up to Xn by definition of 0 and X, which equals 0 plus X1, 0 plus, and this here is a box plus, but this here is our scalar addition, X2, 0 plus Xn. And notice here, this 0 is my scalar 0. This here is my vector 0. Okay, and this is by definition of our addition operator, which equals X1, X2 up to Xn by def of 0 in real addition, which equals X. As X was arbitrary, this is true for all X. What are we doing here? We're considering a general 0 vector. We're considering an object and showing it satisfies the definition of being a 0 vector. And there are 2 axioms in vector spaces that are like this: the additive inverse and the additive identity, showing that the additive inverse exists for every element, and that and then showing that the additive identity also exists. Like I said, we're going to leave this third one as an exercise. We'll move on to question 2. In this question, we are asked to consider 2 subspaces or 2 subsets and prove that they are vector spaces. Now, what we'll notice is that these 2 subspaces or subsets are subsets of vector spaces. Now, because of this means all we have to do is prove subspace. So if we can prove it's a subspace, we proved it's a vector space, because by definition, subspaces are themselves vector spaces. Okay. Now, to prove it's a subspace, we need to prove non-empty and closure. Okay. What we can do is we can attempt to do this for both. Okay. for both our first and our second. And sometimes when we do this, in the attempt to prove closure, a counterexample will come up. And for non-empty, we want to show that it has an element. Now, we can show anything for non-empty, but typically showing the zero is easier because, or is valuable because if zero is in it, it's not empty. Zero is not in it, it's not a vector space. So consider 0, 0, 0, 0 as, and we're adding this entry to this entry, 0 plus 0 equals 0. The matrix 0, 0, 0, 0 is in, and I'm going to label this W, is in W. Okay? And if we look at W1, like in this set, to show non-empty, we consider 0, 0, 0, 0 as 0 times 0 minus 0 times 0 equals 0. This matrix is in W1. So both of them have the 0 vector. So we've got non-empty, but what about closure? Well, in our first example, let's consider, let C be in the real numbers, and we're doing the real because the matrices are defined over real, telling us what our field is. And X and Y being in W. Well, let's redefine what X and Y are then. Then X equals A1, B1, C1, D1. And Y equals A2, B2, C2, D2, where A1 plus D1 equals 0 and A2 plus D2 equals 0. Consider X, CX plus Y. Well, CX plus Y equals C A1, B1, C1, D1 plus A2, B2, C2, D2, which equals CAC1 or AA1 plus B1 or A2, then CB1 plus B2, C1 plus C2, and CD1 plus D2. Here, CA1 plus A2 plus CD1 plus D2 equals CA1 plus D1 plus A2 plus D2, which equals C0 plus 0, which equals 0. Thus, CX plus Y is in W. Therefore, W is a subspace, which is by definition a vector space. Now we want to prove that this part B is either closure or not closure. Okay. Now, what you can do is you can consider two generic elements and a constant and expand it. And what you'll get is you'll get this 0 plus terms plus 0. And it has to do with this multiplication of this AD and BC. But what we're going to do is we're going to consider specific counterexamples, C equaling 1, X equaling 1, 0, 0, 0, and Y equaling 0, 0, 0, 1. Then CX plus Y equals 1, 1, 0, 0, 0 plus 0, 0, 0, 1, which equals 1, 0, 0, 0, or 1, as 1 times 1 minus 0 times 0 does not equal 1, or does not equal 0. CX plus Y is not in W1. Thus, W1 is not a subspace. Therefore, W1 is not a vector space. Now, how did I come up with these? Well, what I did when playing around with this, if I didn't just obviously see it, is I would just take C in R and X and Y in
W1, and I'd write out what it means, and then I expand it. When you write out what it means and you expand it, you could kind of get rid of some things and you can see what your variables could be. And it doesn't automatically give you a result. So then what you got to figure out is what values would give a counterexample. So if you set up this system and you do cx plus y and you don't immediately get a result, and you have these leftover variables, you can use those leftover variables to see if you can somehow create a counterexample.